So what I want to talk about on this one is, I guess, really my theory for why photons and why electrons behave the way they do, why photons are emitted the way they are, and things along those lines. So I'm going to show you what I currently have up here on this drawing, right? And then I'll talk about what this is, but then I'll also try and draw it out as I'm talking about it again. So what I have here is, basically I have two different types of orbital drawn out. So what I think would play out, right, is, okay, this is where I should start drawing. Right, what I think should play out basically is that, all right, so you have in the middle, you have your, basically, oh my goodness. Not now. So you so you have basically in the middle you have just the atom, right? And so what I think would play out here, right, is that you would have, because every atom can have the two electrons, right, in theory, right? So you'd have an orbital that kind of goes that way and is a little more lopsided to one side, or favors one side more than the other. Let me try and draw that better. A little, oh, too much. So it would be a little bit tighter on one side and go wide on the other. And then on the opposite side, you would have basically the opposite, right? And that's not perfectly opposite, but you get the point, right? So what I'm saying is that, so, for the red, it would be like that, and then blue would be, something like this, right? And then, so say this atom had, its electron. I think that at this point out here, that is where it would release a blue photon off at, right? That's when it hits critical mass, as I've talked about in a previous video, right? And that's when the photon gets released. And then down over here, it's in the consolidation phase, basically, right? And then this is the critical mass for a red photon. And what decides what is and isn't, what decides what is and isn't critical mass for a photon is basically that it depends on the velocity of the electron, and when it comes to that's when it comes to emission, it's the velocity of the photons, right, when they leave, that plays a big part in its mass and therefore, its energy and things. And so when a photon comes into, say, an orbital, right, it comes in, and say we have an orange one come in, right, it flies in here. Well, the orange photon comes in, and there's no orange orbital, right? And the thing is that these orbitals are, the blue is like one pole, is like these are like balance points in the system. And so these would be like, if you were to do the calculation to find the gravitational poles, or the equilibrium orbitals, like, so Earth and all the other planets are basically in these orbital like points of gravitational equilibrium. And so if you were to do that kind of calculation and try and find these poles and these points of gravitational equilibrium, you would find that they are at these, I think that you would find them to be at these energies at which photons are both absorbed and released. And these lines of where photons get absorbed and released when it comes to molecular things kind of get shifted, because when there are other atoms in play, right, that will kind of shift how the gravity of the overall molecule plays out, right? And the orbital paths will change depending on the structure of the molecule. And so I have also, drawn out that, hey, this is like basically, in theory, a molecular structure, right, of like, I guess, 3 atoms. So it could be like water, right? So that's like H2O, right? Except not really drawn to scale, but I guess it doesn't matter. So getting back to it, when this orange photon comes in, it has too much mass, right? It has too much mass to get caught inside of the blue orbital, right? It can't get caught inside the blue orbital, right? Like if it goes this way, right? It has it gets affected by the gravity of the atom, but it has too much mass, right, to be able to stay here, right? Like this is not a balance point for it, so it can't stay in this orbital, right? But it also has too much velocity to go here, right? So when it comes in, it has too much velocity to get stuck inside this trap. So if it does get into this orbital, right, like if somehow it were to come in at an angle where it, was flying directly into this orbital, it actually would have too much energy. So what would happen is it would continue out, it would break out, with escape velocity basically, and it would break out into and be released. And if it came in at an angle where, say, it fell into the blue, what would happen is it actually has too much mass. And so if you have too much mass or you have too much velocity, those things combine together to create really escape energy. It's really not escape velocity, it's escape energy, right? So something that is larger requires more energy to have, like, escape, like be able to escape a gravitational thing. So like it's a lot easier to launch a tiny little rocket than it is a massive spaceship, right? So the reason for that is because of, I think basically, energy is really what's the thing that matters, and matter is energy, right? So the orange photon actually has too much mass to get caught inside the blue. And so what happens is it will also kind of continue out and escape, right? And so in each scenario, since the poles are defined as these equilibrium points, you need to have a certain amount of mass. You need to have a certain amount of energy, right? Which we know, right? And the only way you can have that energy is if you have both the proper mass and the proper velocity, right? And if you have the proper velocity, you'll have the proper mass, because they kind of go hand in hand. And so what happens is that if you don't match the proper mass or velocity, like if you don't match that energy, then there's no, like, you may not get immediately released, but you're not going to stay there, right? So what could happen here is instead of it just getting shot out, it could kind of do something like this, right? So if the photon were to be here and it's flying in, it could kind of get stuck in this orbit, and then it could come in and then come around, right? And instead of, flying back around and getting stuck in this, what it will do instead is it will kind of loop around, but it's got too much energy, and that's when it gets shot back out, right? And so it looks like it's getting basically reflected or whatever, but what's happening is as I said, everything's orbital in rotational motion. So if you were to look at this motion play out, what is really happening is that you have your photon here, and you have your atom here, and the atom is moving this way around the photon, and the photon is moving this way around the atom. And so what you end up with is kind of this sort of spin motion that happens, except the photon has enough energy to get launched back out, right? So it's almost like if you've ever done, like, I don't know, maybe if you were a kid and your parents did this with you, like they'll hold you by your arms or whatever, right? And then they'll spin you around, right? And if they let go, you're going to go flying away, right? Because you have basically enough energy to just kind of keep going in that direction. If they hold your hands and then let go while you're not moving, or while you're just kind of spinning around in circles slowly, you're not going to fly around anywhere, right? It's only when you have excess energy, basically, is when you get launched away. And so what's happening there is basically there is a gravitational hold on each other. They're kind of holding each other's hands, but as they come around, right, the photon basically lets go of the atom and gets launched off again. And so that's what we see as this reflection. It's really not a bounce off kind of thing. It's more of a, whoop kind of thing, right? And so we also observe, let me try and clean this up a little bit here. Maybe I'll just go backwards. And so we also observe if this photon was to come in at this angle like this, right? So maybe it comes in here, but instead of continuing straight through, what happens is that it kind of gets affected, right, slightly, but since it's not coming at an angle where it's really at a good trajectory, what happens is it really does more something like that instead. It gets slightly bent, and this is what we call scattering, right? And we know that, well, no, we don't know this. Sorry. And so in my opinion, red is the largest mass, and then blue is a smaller mass, right? So if this blue photon were, if it gets caught in this, or if it flies in at a trajectory and gets locked into this orbital, it gets stuck there, right? But if it flies in like this, right, it is not going to automatically get caught up in this orbital, right? It's going to pass this atom, and then maybe there's another atom over here, right, where the orbital is, set up so that, oh, okay, now it's stuck in this one here, right? And so because there's so many atoms, we observe it all getting absorbed, but I don't think all photons get immediately absorbed by whatever, atom is there. If you only have one atom, every photon that gets shot at it is not going to get absorbed, even though it does absorb at that energy, at that wavelength, right? So what I think happens here is it'll fly through, right? Let me just clean this up again. It'll fly through, but as I said, it'll fly through, but it will get bent more than that of as you can see, it'll get bent to a greater degree than that of the orange photon, because it has less mass. And because it has less mass, it's more affected by the gravitational pull, but it also has more speed, so it's still able to break out, right? But I do think that it should get a little more, it should be bent more than that of a different photon. And so I know that, this is obviously not drawn to scale, so it doesn't look like there's much of a difference there, but I think that there is. And so what I'm trying to say is that, basically. And so, get rid of my mess here. And so pretty much, I think that this is the mechanics that is driving how electrons are moving, for one, and two, how photons are moving. And the reason why, what I think is happening is basically electrons are constantly emitting out photons, right? But the only photons that, like, if the photon doesn't have energy, sufficient energy to be released, right? Like, say the electron is releasing the photons here, right? Honestly, actually, I don't, maybe they're not constantly, like, they're technically, yes, they're constantly emitting, but they're not emitting at this scale. And so what I think is potentially happening is that when a photon reaches its critical mass here, it basically goes supernova, releases a ton of energy, right? We observe this ton of energy as photon emission, as, a wavelength being given off. But I think really what's happening is just tons of photons are emitted from here, right? And we see this spread as the wave that, perpetuates out. And I've talked about how since these photons are moving, they are basically going to, and like all the particles here, they're going to clump these particles together on the front, and then, on the backside, from where they're leaving, there's going to be a lack, because these photons kind of bunch everything up, and as they bunch everything up, then they leave a void behind them, and then this is what creates the electromagnetic waves that we observe. And it's all run off of gravitational principles, but it becomes an emergent behavior that we see as electromagnetic radiation, and we see as a lot more impactful because these photons have mass and therefore impart momentum, and that, has an effect on things. And the fact that there's nothing here, right, that leads to a stronger, that leads to a motion back in this direction, right? And then if you keep having motion back in this direction at the back of all of these waves, then, as long as you have sufficient mass not to be affected by the photons pushing you away, right, then you are going to get overall pulled in by the magnetic waves. And so that's why there's magnetic attraction, potentially. Not really something I was trying to cover here, but basically I think there's this potential duality. So you have two opposite orbitals that kind of counterbalance each other. And so, on this drawing, I only put one side of it, but really there would be like a second side over there, right? And then, so there would be a separate drawing of basically the exact same thing, just flipped to the other side. And then this kind of leads into molecular orbital theory, which has been proven to be more accurate than the general orbital, like Lewis dot structure or whatever. So it's been proven to be more realistic, right? And this gets back to orbitals and orbital theory. And these orbitals are not the same as like loops like this. They're more like clouds, really. This molecular orbital theory is really more like molecular cloud theory. I think is maybe a potentially better thing, because it's really clouds, just like just like atoms have electron clouds. The molecules then kind of form like electron clouds around the whole molecule. And if you need more information on that, I recommend you go watch someone else, because that's probably not the best description of that. Right, but so adding more mass to one of these bonded atoms in the molecule will cause there to be like a blur or change in the orbital paths of these electrons, and therefore it'll adjust where their critical masses are, and therefore adjust what their escape energies are, basically, and therefore adjust where they absorb and release energy at, right? And so what can happen is that in this, so we've got we'll say our two atoms here, and then another one like this. And this is just how I drew it, so that's what I'm going to kind of follow. And say we have, our red orbital path kind of does initially it was something like this, right? But what happens is it's really more like something like this now, right? Where it does that, or maybe even it does, one of these, and that's so you get I'm gonna add another set of atoms on the other side here. So what you could potentially have happen is something that looks more like it's I really I don't even exactly know, but it could be something like that, right? Where basically it's it goes around, just something like this. There's a loop-de-loop there, comes around, and then back into this, right? And so this actual orbit is very bizarre, right? But it holds it in like this stable lock, right? And the more atoms you add into this, right, then now there's another atom here. So then this path, instead of going that way, would do something like this, and then come back around, and then it comes around, and then it would go this way, right? So now you've got another loop-de-loop kind of coming into this, right? And if you increase the mass of this atom here, right, this is then it also will adjust how this plays out, right? Because now it's going to kind of look something more, it's going to kind of come out and be something more like that. And so now this orbital path is different, right? And because it travels this path like this, right, and it goes farther out, there is a potential that changing something like that will then mean that now, and originally this was the path for like a red photon, right? But now, if a red photon gets that far away from everything, actually, it just keeps going, right? It actually breaks out. But what does get caught now is orange. And orange gets caught, and it'll flow through this path, right? And get be what gets kind of caught here. And red will be able to break free, but orange will kind of get caught up in here. And then if you were to have like blue fly in, right? Blue comes in. Blue's got more energy but less mass, so it comes in and it goes way out here, comes back in, kind of goes way out this way, comes back in. It may even do that instead, right? Come way out again, come back in. But then, when it hits something like this is why it gets really complex really quick, right? Because now, flies out like this, and then it comes back in, right? But which way is it going to go? Well, probably this way, because this is a higher mass. and it's going to go way out here, come back in, and go that way maybe, right? Because it came from, this one came like this, so it went out here, but this one's going to come in closer, so it's probably going to get shot off this way instead. It won't have enough time to turn, and again, you're back at this thing, like, will it kind of follow this trajectory? I don't know, right? But, so you get these really weird energy orbital things, right? And I kind of got a little sidetracked trying to figure out the path. It's kind of fun. But, you know, if you change anything slightly, then it kind of smears where these absorption and release lines are, because there's a certain point where, oh, you know, over here the blue gets absorbed over here, but it gets released over here, right? And so you end up with this kind of weird thing where it's both absorbing this stuff, but it's also kind of what's happening is like maybe it gets absorbed here, but now it's getting released over here, but it's getting scattered because of that, right? And so it's getting scattered pretty significantly. And if anything in this system changes, then that changes where it goes, right? And it could be that since like how this is, right, these orbitals, you know, you kind of get this smearing because it's not necessarily that like these are stable orbits, but they're, I would say, maybe transitionally stable or semi-stable, right? And so, and like photons may be absorbed, right? And they fly around and they get stuck in it for a time, but they do not stay there, you know, permanently, right? So like when it's just a single atom, you know, the system isn't changing really. And so what you can argue is that, you know, if it's absorbing blue, it's always going to absorb blue, right? But when you're looking at molecules, you know, it's absorbing blue now, but it's also, you know, maybe like depending on the motion of all of, like, because all of these atoms aren't just stationary, they're also kind of moving and stuff. And so depending on the positions of these atoms at the time that the, you know, photon flies by, that could affect if it does get released or not, right? And so you could end up with these situations where it kind of smears out where the energy is, because depending on the position, right? Depending on the position it gets released at, it could end up releasing with more energy or less energy. So it could have gone in as blue, right? So it was blue and it... Okay, I don't know. My camera cut out on me. I don't know why it did that or whatever, but so basically, you know, I mean, I don't know. I'm just speculating at this point, but you could have basically it gets slingshotted at this point, so it releases with higher energy. But at this point over here, depending on where it is, it could actually get released with lower energy. So you end up with this smeared line of emission and like different gaps in absorption, because if a photon falls into these proper areas, then depending on, you know, its energy, it could actually end up getting stuck in here for a little bit, even though it, you know, it wouldn't normally if it was just a single atom. But because the orbital paths are so complex and there's so much motion going on, it kind of gets stuck in this trap where, you know, originally it wasn't going to get absorbed, but now it does get absorbed because the dynamics of the molecules. And yeah, I don't know. I feel like I've been talking a lot, and I don't know if I really explained this well. So hopefully I did. Hopefully my camera didn't end up actually cutting out way more than I thought. But in theory, it'll be okay. So I don't know. We'll see what happens. I don't know. I wanted to try this out. I don't know if it'll work or not. We'll see. But I wanted to explain kind of my theory here on this because I think that this makes sense. I think that this could work. I also think this could imply that there could be more electrons in a system than just two, but at any given time, only two photons are like at any given moment, only two electrons. If I misspoke before, I think there's like the balance is two. We think the balance is two because at any given moment they're in a kind of a dichotomy where if one's releasing over here, like then there's usually another one over on the other side to kind of counterweight it, and that holds them in a more stable, orbit and makes them a little less chaotic with their motion. Maybe not. I don't know. I think that these electrons are not really locked into their positions, but I think the reason why spectroscopy is the way that it is has to do with this because if it has the right energy, it gets pulled in or released, and if it's released at that point, then then it's able to break out basically because it kind of gets released on the outskirts. Whereas if it falls in on that path or directly or like slightly inside that path, that's where it gets absorbed. And it's only a matter of time before that plays out. And I don't know. When it comes to emission and absorption, I think this makes sense. I think that this works. I think that it puts into perspective that this is not waves. It makes the photons more physical. It plays on the particle level of photons that we know we observe that as a behavior. And so, one quick side tangent to add on here, because I just thought about it, is that I know that we see supernovas as these big explosions where there's not really anything we see a photon as like a particle, and a supernova is not that, right? And so it's either that they're releasing tons of photons, right, or it's that supernovas are releasing a particle. We just don't observe it because that would be in the dark matter realm, and we don't see that. Potentially, I don't know. Maybe I'm like starting to lean towards maybe that's not what dark matter is, but I'm really I think that I might be wrong on that potential theory that I have. I don't know. I have to make the video for that. But I just want to kind of mention that I know that it doesn't seem to make sense, but I think that it does. So, I don't know. I guess just trust me on that. Anyway, I think that's it. So, peace out.